So it's a pleasure to have the opportunity to present to you today on the topic EBRAINS Digital Twins, Actionable Multilevel Health Data. And as mentioned in the previous presentation by Jan Biale, we experience a challenge that we have to deal with multiple data types if we want to understand the brain. The brain is complex, it's organized as an adaptive dynamical system, and it yields many possible observations at different spatial and temporal scales. And here you see a couple of examples also mentioned by Jan. There's a molecular scale, and of course there's a whole brain scale and many levels in between. So the challenge is to make sense of these different snippets of information, and to understand how they are linked together and yield the function of the brain, but also how they are linked to diseased brains, and how we could intervene to prevent brain disease. So here in this study that has been published in eLife, it's an output of the Human Brain Project. We showed how from data, when we integrate them in complex brain models, brain network models, we can understand mechanisms of brain function. So the model simulates what we can actually measure in real life, and the simulations are shown here in the upper panel and also on the left video. And the measurements themselves, the snapshots, are shown in the lower panel. And they consist of multiple snippets coming from different methods and even from different species. But the model can create a theory that makes sense of all these different and often independent observations. So for example, here you see at a very fast time scale the relationship between neuronal firing, action potentials, and the local field potentials, the potentials of the neuronal membranes. Or you can simulate the ratio between inhibitory and excitatory postsynaptic currents in neurons, or the relation between EEG, electroencephalograms, and magnetic resonance imaging activity, or the so-called resting state dynamics and functional connectivity changes that evolve over several minutes in the brain. Yeah? And these different measures are all simulated with a single brain model. So in this study, we built from real data models of 15 individual healthy adult brains. And a single model can encapsulate these different types of data and observations from the time scale of a few milliseconds up to a time scale of many minutes. So this is a brand new publication, also an outcome of the Human Brain Project. It came actually out yesterday. Brain simulation augments machine learning-based classification of dementia. And it shows how inferring states that cannot be measured from the actual data themselves helps us to come closer to the mechanisms of disease and to mechanistic biomarkers that then help in classification of the data and classification of different disease groups. So we can use the model augmented integrated data as computational microscope to enrich the feature space that we obtain from experimental data and increase the discrimination and prediction accuracy. But as you may guess, many skills are needed for this type of research and this type of complex data integration. and also many types of different data. And EBRAINS helps to reduce the complexity. It provides well-organized and documented tools and data. For instance, the Virtual Brain Cloud Facility Hub provides access to brain simulation in the cloud. So you see the related publication here on the top of the slide. And it makes maximum use of the various services of EBRAINS by making them work together. And in the publication, you see the number of authors, which is quite large. So this is really collaboration and action that is happening in the Human Brain Project to achieve this degree of integration and interoperability between the different components that are required for data integration and for gaining knowledge from the data. But the brain data are also at the same time health data. Yeah? So they obtain or comprise very personal information, and therefore they are sensitive data according to the general data protection regulations and the European Union. They are classified as special category of data, of personal data, and they need proper protection. And in these workflows that you see here, we have already included such protective measures like end-to-end encryption, access control, and sandboxing. And this diagram here looks pretty complex, but what it shows is just the tools that you need, shown here in blue on the right side, for personalized brain simulation are actually integrated and interacting with the core functionalities of EBRAINS. Yeah, so you have the high-performance computing backend, you have the cloud of EBRAINS, and you have the data storage and other tools. And the services are directly interacting and making use of this existing infrastructure. And they are not only interacting with the core infrastructure, but also with other tools and components, like the digital atlases of EBRAINS or the neurorobotics platform shown here on top. And the communication typically occurs through RESTful APIs, so standard type of interfacing components. The Health Data Cloud now is a relatively new project in the Human Brain Project that brings the service for sensitive data on a new level and at a new scale. Yeah. So here you see the central hub of EBRAINS, basically the central IT infrastructure. Many of the core services are provided by the Swiss supercomputing center CSCS. There are other supercomputing centers also providing resources. But in order to handle sensitive data like health data, we are striving for a federated system that interconnects with the different satellite nodes, the hospital data centers. So here on the left, you see now an example of the Charité data center in Berlin that provides already service for sensitive data. So in the past 3 years, we have established there's a so-called virtual research environment. So this is a secure and protected infrastructure for personal health data. And the Health Data Cloud now integrates the different nodes or data centers so that the metadata that are generated decentrally, so apart from the actual central EBRAINS infrastructure, can be transported and ingested in the knowledge graph that you just have seen, yeah, the knowledge base of EBRAINS that makes the data fair and discoverable. And with this integration, there's a single entry point for users to discover data that are not only stored on the central infrastructure of EBRAINS, but that are available decentrally at other satellite nodes like the Charité Hospital Data Center. On the other hand, EBRAINS develops many tools and services, and several of them, including those required for personalized brain simulation, are available as containerized software. This means that the software can be executed on any system. It's not system specific. And the Health Data Cloud allows to ship such containerized software from the central hub to the decentral satellite nodes and to run them on the data. So it is actually not required to ship the sensitive data to another data center. It is possible, but it is not required. But you can also decide to ship the code to the data and do the processing decentrally. And the Charité is not the only node. There's another already existing service for sensitive data is located at the Oslo University Hospital. This is just another satellite node of the Health Data Cloud. And it follows the same principle. The metadata are going to the central knowledge graph of EBRAINS and are made discoverable to users via a single entry point. And code can be shipped to the satellite, and processing can happen decentrally to data that are stored here. But sometimes the satellite nodes and hospital centers lack actually the compute infrastructure that is required for complex simulations and data processing. So not each hospital IT center or data center has the high performance computing clusters that are required. And in these cases, we integrate with other supercomputing centers and provide the possibility to ship data to the place where the resources are available in a secure way with full end-to-end encryption, and to do, again, the processing decentrally. But at the core of the Health Data Cloud is the architecture of the virtual research environment that has been developed in the past years at the Charité as part of a European Open Science Cloud project that was also a partnering project of the Human Brain Project. And this virtual research environment provides a protected space for sensitive data, and it has undergone an audit, a data protection audit, to show and demonstrate its GDPR readiness. And this is how such a system looks like, a virtual research environment. Yeah, it provides different functionalities. So for example, it provides to researchers workspaces or workbenches to access the data in the data center, and to also bring in their own tools and algorithms. So basically, if they have a software or also a desktop application, they can run it within this virtual research environment. There are special overly protected zones for sensitive data that still have primary identifying information. And then there's a core zone that still has all the protection mechanisms for sensitive data that are indirectly identifiable. Yeah, for example, brain data can be identified not because the name is in the images that can be removed, but because of the uniqueness of the anatomy and also the function of the brain. And therefore, the data remain highly sensitive. They cannot easily be anonymized, and they would lose the potential for personalized medicine and precision research. And they also cannot easily pseudonymized. Yeah? So anonymized means that there's no way to trace them back to the identity. Pseudonymized means that there's still a protected key that allows backtracking of the identity of the data subject, but it is protected. And in the case of brain data, the actual identifying information is still in the data, so it's not even protected if you are working on the data. So it's highly sensitive, and therefore it needs such special treatment. This virtual research environment can also come with interfaces to hospital data sources or other data sources. So for example, at the Charité, we have direct interfaces to the scanners, the clinical and the research magnetic resonance imaging scanners, and also other hospital data sources. And of course, there's also interface to high-performance computing to provide all the compute power that is needed for complex simulations and analysis. And a new infrastructure project funded by the European Commission, Horizon Europe program, is just starting. And it integrates with many different data sources across Europe. For example, there's a collaboration with the European Platform for Neurodegenerative Diseases that is led by Petra Ritter, EPND. And he's also a partner in EBRAINS Health. So we really look for partners that generate the data sources that then interface their data with infrastructure, also their infrastructure that they build with infrastructure that is built in the context of EBRAINS and the Human Brain Project. And the goal is to streamline the data models, what you have seen in the previous presentation, with models that are used in other large research communities, so that the data and also the tools become interoperable. And I show you here a few examples how various types of data and knowledge can be integrated with the help of EBRAINS. Now, for example, we can map pathway inventories on the brain. So pathway inventories are also organized in knowledge graphs, but they contain slightly different information than the knowledge graph of EBRAINS. And by mapping them on the brain and the spatial reference the coordinate system of the brain, we can use them to parameterize our models and simulate the effects of changes of such signaling cascades, for example, in brain disease. We do this at the Charité specifically for dementia and different kinds of dementia like Alzheimer's disease, Parkinson's disease, and others. But we can also interface with data coming from anatomical and cytological atlases that are available in EBRAINS. And there are the interfaces to directly draw these available various data types into our brain models. So here you see an example on the right side. These are receptor densities that are available via a RESTful API in EBRAINS, and we can map them in the brain model, and also different layers. Yeah? We can take into account different types of receptor distributions, and this will inform the parameterization of the model, and hence make the model more biological plausible. So the more we integrate data of various sources, the more biological realism we achieve. And last but not least, we can not just integrate the data in biophysically meaningful models of the brain or of neuronal networks, but we can also embody the model with the help of EBRAINS and the Human Brain Project by linking it to the robotics platform that is also part of EBRAINS. So what you see here is an example, and the brain model is interfaced with the robotic simulation platform and directly controls the movement, the behavior of the hands. And what has been performed here is a popular task that has been studied extensively in experiments, and it is captured with our model, the virtual brain, what is really observable in real life. But the model, the mathematical model, also delivers a theoretical explanation for certain principles of finger movement, for example. A very exciting development is multi-scale co-simulation, also being developed in the Human Brain Project and EBRAINS, also related to data integration and making data actionable. So that means that different parts of the brain are simulated or modeled at different degree of detail. Yeah, the simulation outputs are then compared to different data types again. For example, at the fine scale to the firing of neurons or local field potentials or inhibitory excitatory postsynaptic currents. And at the coarser scale to, for example, EEG, MEG signals or functional magnetic resonance imaging. And for this, we interface different simulators. For example, the virtual brain, the whole brain simulator that simulates at the resolution of functional magnetic resonance imaging or electroencephalography, with more detailed simulators like NEST, Anarchy, Neuron, that simulate the smaller parts of the brain with more detail. For example, the spiking of individual neurons. And this has been actually put to test in a recent study that has also just recently published in the European Journal of Neurology, where we apply multi-scale co-simulation to brains of Parkinson's patients. And as you can see here, we stick a virtual needle for virtual deep brain stimulation in these brains. And thanks to the co-simulation, we now can monitor at very fine detail the activity in the relevant subcortical structures, the basal ganglia, the thalamus in this case, but also at a causal scale in the remaining brain, for example, the cortical regions. And this is a tool that might, if tested and validated, be very helpful in the future for planning on an individual level the best possible treatment through deep brain stimulation for an individual patient. The EBRAINS platform has presently an impressive number of more than 5,000 users from 75 countries. And as you can see, Denmark is not yet under the top 10 countries, but of course we hope with the event today, we increase also the traction in Denmark. Interestingly, only 2% of the users of EBRAINS come from the private sector, so 98% are academic users. Nevertheless, EBRAINS, with its unique infrastructure, of course, has certain capabilities to provide federated testing and experimentation facilities that can not only accelerate the academic research, but also potentially brings what is required to make health, AI and robotics products ready for the market. Yeah? So to make data, health data really actionable, they need to become a product that is used in the clinical everyday life. And EBRAINS has the potential to close that gap in the innovation chain for health, AI, and robotics. There's a large gap before the data really lead to tools that help patients, and providing the opportunity to the private sector to make products trustworthy. Yeah, this was also a key word, trust, mentioned in the previous presentation, and to make the product certifiable for the market in Europe with its very strict regulations, which are good, but which also are a very high barrier and hurdle for the private sector to bring their products, their health products to the market using new technologies like artificial intelligence and robotics. So we hope that EBRAINS will be attractive for academic users, but also may become a mechanism to help accelerating bringing health products to the patient. And the subject of health data, and in particular the global health data space, is also a central topic of the upcoming World Health Summit that is held in Berlin, where also my institution is located. And there we will discuss with various stakeholders from all parts of the world about the present state of health data sharing around the world, but also the present barriers and how we can resolve them. And I think with this I come to an end of my presentation. I thank you very much for your attention. And of course, I'm available now for your questions.